Hi guys, so this is lesson 4 on chemical bonding, and in this lesson we will be talking about electronegativity in the periodic table. Now in the previous lesson we looked at covalent bond formation and we looked at simple molecules like hydrogen, oxygen and nitrogen. We specifically looked at an example of hydrogen atoms coming together to form a molecular orbital and subsequently a covalent bond. Now, these examples are quite simple because both hydrogen atoms are the same, and therefore the attractive forces that they will exert on their shared electrons will be the same. However, many covalent bonds form between two different atoms, and then it becomes more difficult to determine how those electrons will be shared, because not all electrons will be shared equally. Like we said, we can think of it like a tug of war. But if you have a really big, strong guy pulling against a really skinny guy, the big, strong guy is probably going to win the tug of war. Now, in chemistry, we also have big, strong guys in terms of our tug of war around our shared electrons. And a useful way to determine which guys are the strong guys and which ones are the skinny ones is a scale that was developed called the electronegativity scale or electronegativity values that was assigned specifically by Linus Pauling. Now there are many electronegativity scales that was developed, but Linus Pauling's one stuck. Now what is important is that you realize that the values here don't have any units and that it wasn't assigned by looking at the bonds that form between two atoms and how strong they will attract those electrons that they share. So the first important thing that you need to take note of is the definition of electronegativity. Electronegativity is defined as a measure of the tendency of an atom in a molecule to attract the bonding pair electrons. Okay, so let's break it down. What does it mean? A measure, so it gives us an indication of how strong an atom that's within a molecule will attract the bonding pair electrons. Now let's maybe just talk about that word bonding pair electrons. Okay, what does it mean? So if we think of our example of hydrogen, the electrons that were shared between them, those electrons there, we call them a bonding pair. It's two electrons there for a pair, and they are responsible for the bond that forms. So they are our bonding pair electrons. So electronegativity tells me how strong does each of these atoms attract these shared electrons. Now in the case of the hydrogen molecule, we've got the same atoms, and therefore they will attract those electrons with the same amount of force. However, let's take, for example, something like a hydrogen fluoride molecule. And I'm just going to represent the bonding pair here still with two electrons. We will do Lewis dot diagrams later on where you will learn how you can represent a covalent molecules. Okay, in this case, fluorine has got 9 protons, whilst hydrogen only has 1 proton. Now remember, it's the nuclei that's attracting these shared electrons. Fluorine has a lot more protons, so what do you think will happen? Fluorine is probably a big fat guy, and hydrogen is a skinny one. And fluorine will probably win this tug of war. Now, this is what we are going to look at when we look at electronegativity values. If atoms have higher electronegativity values, they will attract bonding pair electrons stronger, okay, or more. And in the case of Pauling's scale, fluorine has the greatest electronegativity with a value of 4.0 assigned to it. And all other elements' electronegativity were calculated in relation to this value. So the table that we have here, you will see it's color indicated as well as with numerical values. Fluorine is on the highest end. And what do you notice in terms of the trend? As we move across this a period, you will see that there's an increase in electronegativity. And if you move up a group from the bottom, you would see there's an increase in electronegativity. So the electronegativity values tend to increase towards fluorine. So if you would say the other way around, it would increase across a period from left to right, but it would decrease down a group from top to bottom. Okay, but we will discuss these trends. To discuss them, I once again want to take you to our graphing program that we could access to see how these trends look for the different groups and periods. Okay, so here once again we have our periodic table, and we can look at the trends by clicking on these arrows. So let's first discuss the trend in electronegativity across a period. Now I want you to look at the numerical values. You will see that there's a clear increase as we move across period 2. Here then is our graph for the trend in electronegativity across period 2. Now you will see that there's a very linear relationship of an increase in electronegativity as we go from lithium, which is in group 1 in period 2, to fluorine, which is in group 17 in period 2. Okay, now why is this the trend? This is the question we have to answer, and this is what you will be required to explain in tests or exams. Once again, let's look at our atoms, okay, and our electron configuration. So in the case of lithium, lithium only has 3 electrons, so that would be its electron configuration. So if we were to draw a diagram, we would see that there is our first energy level, and this would be our second one. In the first one, we've got 2 electrons, and in the second one, we only have 1. If we go on to, let's say, boron, boron has got 5 electrons, so it's 1s2, and then it's 2s3. So we're still only in the second energy level. Okay. However, our nucleus now has 5 protons versus lithium's 3 protons. We also still have our electrons in the second energy level, and I've made a mistake there once again. Don't know why I do it constantly. So it should be 1s2, 2s2, and then 2p1. That would be the correct way to write it. I think I'm just thinking about the 3 electrons in the second energy level and not of the orbitals. Okay, so that's our second energy level, and now we have 2 paired and 1 unpaired electron there, and there's our 2 paired electrons. But we've got 5 protons. If we go to fluorine, it's 1s2, 2s2, 2p5. So now we've got first, second energy level, and we've got 2 electrons there, and then we've got 2 of them paired, 4 of them. Okay, so that's 4, 5, 6, and then we've got 1 lone one. Okay, so what I want you to notice is that in the case of fluorine, we will have 9 protons. Now guys, as we discuss the trends with first ionization energy, there's a similar pattern here. Okay, we have an increase in the nuclear charge. So there's an increase in the nuclear charge. Okay, remember, what is the nuclear charge? The amount of protons would be equal to the nuclear charge. As there is an increase in the nuclear charge, what do you notice around the energy levels which the valence electrons occupy? That's correct. They're all the same energy level. So the valence electrons are on the same energy level. That means they are a similar distance from the nucleus. But now the nucleus for fluorine has a greater nuclear charge than the one for lithium. So one for fluorine can attract those electrons more strongly. And therefore, if I try to pull those electrons away, or if I'm in a tug of war with fluorine, then I will lose it if I'm lithium. That's why lithium, if it's an ionic bond, would form a positive ion, and fluorine would form a fluoride ion, which is negative, because it wins that tug of war. Okay, so why does electronegativity increase across a period from left to right? Because there's a greater nuclear charge, which means there's a greater force of attraction on electrons, the valence electrons specifically, in the same energy level. And therefore, your electronegativity values would increase. Now we're going to look at the trend in electronegativity values down a group. So this is group 17 that I've selected. So there is fluorine, and you will see that there's a clear decrease in electronegativity values as we move from the top to the bottom in group 17. And this trend is the same for the other groups as well. And once again, we want to ask the question, why? Okay, now, yes, it is true that if you look here, we've got an increase in atomic number, which means a greater nuclear charge. However, there's a problem. What is the problem? As we move down a group, what happens? We get new periods. So, and every new period that we have means there's an additional energy level which electrons can occupy. So fluorine is 1s2, 2s2, 2p5. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. If you go to bromine, you have a lot more electrons, and you're going to have electrons up to the 4th energy level. If you go to iodine, you will have electrons up to the 5th energy level. And if you go to astatine, you will have electrons up to the 6th energy level. Okay, so as you move down a group, you have electrons occupying higher energy levels. Higher energy levels mean that the electrons are further away from the nucleus. So if that is fluorine, this one would be chlorine. So now the distance between the nucleus and the valence electrons are increasing. And what else? Yes, we learned about it in the previous video on first ionization energy, topic 3.2. There's more electron shielding. So with increased electron shielding, it means that the force that the nucleus can exert on those valence electrons becomes weaker. So the distance is greater, there's more electron shielding, and therefore the electronegativity values would decrease. So to recap, if we look at our notes, electronegativity trends down a group on the periodic table. What happens with the values down a group? The values generally decrease. Why do they decrease? Even though the number of protons and electrons increase, there are more electron shielding because you have more energy levels, which limits the attractive force of the positive nucleus on those valence electrons. The electrons are also further away from the nucleus. So, an atom with fewer energy levels will be able to exert a greater attractive force on the shared valence electrons if a molecule forms, and therefore the higher up you are in the periodic table, so the top of the group, you've got fewer energy levels, so those atoms will have a higher electronegativity values than the ones lower down, which have more energy levels, more electron shielding, and therefore a weaker attractive force that they can exert on those shared electrons. If we look at the electronegativity trends across a period from left to right, we see that there's an increase in electronegativity. Okay, all the electrons are on the same energy level. However, as the atomic number increases, the positive charge of the nucleus increases. And as such, the nucleus can exert a greater attractive force on the electrons, which are all in the same energy level. Okay, now guys, there's one question which we haven't answered yet. And this question is posed here on page 15, where it says, the noble gases are not represented in the table above. Why? Okay, you would see that in some tables with electronegativity values, they do represent the noble gases, but there are no values indicated. Whilst here, you see them, you don't see them, and it only stops with group 17. Now, why is that? First of all, what do we know about the noble gases? They are inert, which means they don't react. They don't necessarily, in normal circumstances, form compounds. Only under special circumstances, they will form molecules, and there's only a few of them that will even do that. So those circumstances are so rare that we couldn't determine their electronegativity values. And therefore, they don't have electronegativity values because they don't normally form molecules. It is important also that you note that you only have to